So 2-3, we had two sections last time. 2.1 basic definitions and introduction. 2.2 we did arc lengths. Now today we'll do the curvature and Frenet-Serret. So very important section. Okay. So here, actually, alpha, then S, that is unit speed. So everyone knows what that is. Unit speed, right? What is that? Derivative? Derivative? Magnitude of derivative is 1, right? So that is 1. So we had the arc length parameterized. If you have a parameter, arc length parameter, then we learned that is the curve becomes unit speed, right? Right? Mm-hmm. Okay, then with that, actually let's define the curvature. So we define the curvature we use this notation kappa and we use parameter S. Then this is magnitude of T prime S. Do you remember big T? The unit tangent vector field, right? Actually is actually here. So big T this case is alpha prime S. If it is not unit speed, we have to divide this by its own length so that we can make a unit. But this is a unit already, so big T is simply the derivative of original curve, right? Mm-hmm. Then we define the curvature as the magnitude of the rate of change of this big T. Okay. So this makes sense if you consider two examples after that. So what is your impression if you hear the curvature of a curve? Curvature.
How curvy it is.
Like curving? It measures how much it curves, right? How much it bends, right? So we'll see. Okay, why? From that, there's two examples. So first one, let's consider a straight line. So u plus tv, we take v is non-zero and uv is a constant vector. So this is a parametric equation for a straight line, right? Right? This is a direction vector. This is constant vector. It goes through, right? So if you see here, then what? U is a vector. Let's say this is u. U plus any constant multiple of v vector. So u plus v. Let's say this is v, then that will make that point. U plus 2v, then there will be this point. If you take minus value for t, it generates point the other direction. So there will be the straight line like that. That goes through the vector u, and direction vector is v then. So this is v. So that is the equation for the straight line. Okay? Then to use this definition, actually we have to consider a unit speed curve. I mean the arc length parameterized curve. So let's change it, change the parameter. So what is arc length function? S. Integral t0 to the t magnitude of alpha prime t dt. Is that right? But here we can put this one as a 0. If t0 is not 0, we can translate, we can change the interval so that it has a 0 in it, right? Just by translation. So then if you put this, what do you have? V dt. So V, so what do you see? V dt, right? So what is t? So S is Vt, so t is S over V, right? So let's change the curve in terms of S. Then U plus T S over V and V, right? Make what? S over magnitude, I forgot. Yeah, that sounds, yeah. Okay. Okay? So there will be this. Okay? Then what is big T then? Big T in terms of S. That is constant. So it's V over magnitude over V. Right? Respect to S. Then now we take the one more derivative to figure out, to find the curvature. So derivative of big T, that is 0 because this is constant vector, right? So what is the curvature? 0, right? So you see, that straight line doesn't bend at all. So it makes sense, right? Then another one. Let's see this one. R cosine T, R sine T 0. So what is that?
This is like a circle.
That's a circle, right? In xy plane, the radius r, right? We take our positive constant. Then let's see, alpha prime t. It is minus r sine t, r cosine t, 0. Then magnitude r, right? So what is arc length? 0 to t. The magnitude of this goes to r, okay, there. So it's rt. So similar to that case, actually t is s over r. So we reparameterize this circle with the arc length. So r cosine s over r, r sine s over r, and 0. Then it becomes unit speed with the change, arc length parameterization. You can see that is 1 over r comes down and multiply that by r, that cancels. So it's minus sine s over r cosine S over R 0. So this has length 1. Okay. And this is a big T. Right? Then what is the derivative of that? One more derivative. Minus 1 over R cosine S over R minus 1 over R sine S over R 0. Right? Then what is the curvature then?
1 over R.
Right, magnitude of that is 1 over R. Right? What does that mean? We have a circle, right, of radius R, and then curvature becomes it's constant, right? So the circle actually it changes, it bends, it curves in a constant manner. If you change it, if you detect, if you see the rate of change of tangent, it bends in a constant manner, right? Also, if you compare the value of R radius, if R is radius is big, if radius is big, then it curves slowly, right? So curvature becomes smaller, right? If R is small, it changes quickly. So it's inversely proportional. Right? It's 1 over R. That makes sense? Okay. Okay, then. Right. Okay, then I like to actually view this curvature differently here. Another view of curvature. Okay, we consider plane curve. Lying on the xy plane. Okay. And then is arc length parameterized. Okay. So alpha prime s is x prime s derivative. Okay. So if you graph it like that, at each s along the curve, we are going to define something out of it. So if you select that point, at this point, we have a tangent vector, the derivative of alpha, right? And at this point, we draw horizontal line like that, parallel to this, okay, at this point. Then we see angle between this horizontal line and tangent vector at the point. So we define this is theta s. So theta s is angle between tangent vector at the point s and horizontal line. Okay? That makes sense? Okay? Mm-hmm. So we have actually two vectors, and theta is the angle between two vectors. So if you remember before from calculus V, if you have two vectors, A, B vectors, Then we have an angle theta between two. Okay. Then we have this formula, cosine theta. Do you remember that? Eh? A dot B, right. A dot B, dot product, magnitude of A, good. Magnitude of B, right. This is a dot product. This is a multiplication. Okay. So we'll be using this formula for that. So if you apply this one to that, we have a cosine theta S. Then we need the two vectors. So one vector is obvious tangent, and we use a I vector, 1, 0, 0 vector. Okay. So that is dot product T. Let's use this one. Sometimes I use this notation for dot product. I use this one. Either way is okay. Okay. So and 1, 0, 0, 1, 0, 0 I. So this vector is I vector divided by what? Magnitude of T and magnitude of right, which is 1 already. So is what?
Just the
Magnitude of T. Actually, what is that? This is T. So this is a 1, this is 1, so actually it's 1 times 1. If you take the dot product of this T and 1, 0, 0, what do you have?
Just the
X prime. So we have here big T is now X prime is a cosine theta S, and what is a Y prime? What is good candidate for the Y prime? By the fact that this is given as cosine theta and the length of this one is 1. Sine, right. It comes on together. Sine theta is. That makes sense?
How do you get the sine again?
Because length is 1. Length of that whole thing is 1. And then we figure out this is cosine. So this is sine, right? Because cosine square theta plus sine square theta is 1. Right? So we use this part for the sine theta. And now we are ready to get the curvature. So what is T prime S? Negative sine theta S, theta prime S, chain rule, cosine theta S. Same theta prime S, 0. Okay. And now curvature is magnitude of this by definition. So we take out theta prime S outside, and there will be times theta prime S. Take out that one and apply the magnitude. Right. This one is a unit speed, length 1, and that is the absolute value of theta prime. So that means this shows what? Curvature can be viewed as interpreted as the rate of change of the angle between tangent and the horizontal vector field. Rate of change of the angle. Okay, so this is I like that one. Actually, this is the idea of Euler. Okay, yeah. It's simple, but it's very neat, right? So we define the curvature as the rate of change of the tangent. Also, you can interpret as the measure of the rate of change of the angle between the tangent and horizontal line. Okay? Is that okay? Any question? All right? Okay. Then we have several definitions. So we'll define two kinds of normal vector fields. Principal normal vector field. So we'll be using n, big N. This is defined as T prime x divided by curvature. Okay, is a unit because if you apply the magnitude of T prime s is a curvature. So that is a unit. Right? And it says normal, then we'll see why is normal soon. Another normal is the binormal vector field. B of S. That is defined as a cross product of these two. Okay, so we have a T tangent, unit tangent vector. We have a principal normal vector field N, defined this way, and we have a binormal vector field, binormal. By taking cross product of T and N. We learned from calculus 3 that if you take the cross product of these two vectors, then resulting vector is orthogonal perpendicular to the original two vectors. So this is orthogonal to T, and that is orthogonal to the N, right? So that makes sense. But why that N is normal? This is orthogonal to the T as well. So we'll see, but we can do it here. This is a normal, N is a normal to the T because of this fact. T, right? Because this one is square of the length of the T. Do you remember that? Right? Then we know that is a unit, so that is 1. Right? Then we can differentiate that. We can differentiate dot product. We do the product rule as well. So the way we differentiate the dot product is simply the product rule. So take the derivative. Take the derivative to this. So that the derivative of that is derivative first, leave the second same, plus leave the first the same, take the derivative. Okay? Then what is derivative of 1? That is a 0. Right? Then what is this? Inner product of t and t prime is the dot product, I'm sorry. Dot product of t and t prime is same as the dot product of t and t prime. Right? Right. So this one is 2t. So dot product of t and t prime, actually you can ignore 2. Dot product of t and t prime is 0. Right? Then what is t prime? T prime, by definition, T prime is curvature times n. Right? So we replace this by curvature n. So the T curvature n is 0. Then K is a real valued function. So we can take K out. So there will be dot product of T and n is 0. Right? Then we assume curvature is not 0. If you assume curvature is not 0 anywhere on the curve, then what do you have? T and n, dot product of T and n is 0, which means T and n are perpendicular. Right? Okay? So we have a T and B. Then also we define another one. We define torsion tau. This is defined as dot product of actually minus. We will see the reason why we have a minus in the definition. It's dot product of B prime and n. So real valued function like a curvature. Okay. So it's a B prime, that B, and dot product of B prime and n with minus. So it's a real valued function. Okay? Okay? So here, then we have 1, 2, 3, 4, or next one. Is that? Recall the following is Frenet-Serret apparatus. We have a curvature. We have a torsion now. We have a unit tangent vector. We have a principal normal vector field. We have a binormal vector field. So these are called Frenet-Serret apparatus. And here, T and B, we call Frenet-Serret frame. Frenet-Serret, two Frenchy mathematicians found that one. It's very powerful and useful tool to study curves in RSP. So here is the example. So we have a big T, alpha prime S, which is cosine S over R, 0. That is alpha prime S, because it's unit speed. And what is the curvature? Actually, T prime. Right. Curvature, we have, this is 1 over R. Take the one more derivative, right? We have a T prime S So it's a minus 1 over r cosine x over r minus 1 over r sine x over r 0. So magnitude is the curvature, so we have that, okay? Then what is n? What is principal normal vector field then? N is P prime S over curvature. So what? Yeah, this divided by that, so this is gone, right? 1 over r is gone, so that is minus cosine s over r minus sine s over r 0. That's n. Then what is b? Cross product, t cross n. So let me write t there to see better. Minus sine So if you take the cross product, what do you see? 0, 0, sine square s over r plus cosine square s over r, which is 1. Okay. Okay. Right? So we have a curvature, we have a T and B. So what is the torsion? Huh? Torsion is defined as a dot product of B prime and N. So what is B prime? B prime is 0. Okay. So if you graph it, actually here's a circle, and at this point is T, that T. What is N? N is pointing. Difference between N and original curve? What? It is is a cosine s over r minus cosine and sine. Same thing, similar, except r. But what? If this is the r power s, then what is n? Inverse, right? So n is this. And also is orthogonal, right? So if you take the dot product of this and t, you see sine s over r cosine s over r minus sine s over r cosine s over r, which is 0. So dot product of t and n is 0. Right? So that is t, t and n, t and n, t and n. Like that. Okay? Then what is B? Yeah, it's coming out of a board. B is a K vector. B is K vector, as you see. So, what does that mean? Actually, B and the torsion measures how much the curve lies away from a single plane. Actually here, this is this circle lies in a single plane, and the B, we figure out B is B, how much B changes along the curve? It stays the same, B doesn't change. B stays as constant vector along the way, right? Okay, so that is the example. So at each point of the circle, actually you see this is a T and B. So it plays like a XYZ axis. But XYZ axis stays the same, it doesn't change it. But along the curve, you see, T and B are changing, right? So we call T and B the moving frame because it changes along the curve. So it's a Frenet-Serret frame, so we call it a moving frame. Okay. Okay. Is everything okay so far? Okay. Then here is another one. Where is it? So let's see this. And R and H positive, constant. Let's see. Sorry, that is 1 over. Okay. So what is T? Let's see whether that is unit speed or not first. Minus R omega, then R omega cosine, then is H omega, right? Then what is magnitude of that? The square of that plus the square of this plus square of that, right? So it's R square W square plus H square W square. So R square plus H square and W square. That is omega or W, then you can go either way, that is 1, right? We set omega that way then. Okay, to make that one is unique. Square root of, right. Yeah, okay. So that will be this big T. After we figure out that is unique, right? Then what is the N then? To get N, we need a T prime S. So another omega comes out, right? Minus R and that is 0. So what is the curvature? Actually, with the square and square, add them, right? And take the square root. So R R squared. Oh yeah. Okay. So where is the yeah, right. Thank you. Oh no. It's S. So only 1 R. Yeah, no. Right? So what is the magnitude of that? It's R omega squared. Right? Then what is N? We divide this by that, right? So that is minus cosine omega S minus sine omega S 0. then it's similar to the one that we had on the circle. Actually, what is that? If you graph it, yeah, circular helix, right? The xy makes a circle, but as it goes up, this is z changes, right? So it's circular helix. So if you project this on the xy, there is a circle like this example, but it goes up, right? So curvature is what? Curvature of the helix? Constant, right? Actually, this one is r over omega squared, right? R squared plus h squared, and RH a constant, so that is constant. So if you imagine the circular helix, it changes, it circles, it changes in a constant manner, right? It bends, it curves, yeah. Then this is n. Then what is a b then? T cross n. Can you see? Can you take the cross product of t and n? Let me copy this here. Taking cross product of t and n, right? So, what do we need next then? We have t and b, we have curvature, and what is missing? Torsion. Torsion is a minus of dot product of b prime and n. So we need b prime. Minus h square cosine omega square and 0. And dot product with this and n. So if you take the dot product,
Shouldn't that be positive?
minus is a what? Plus? Oh yeah, okay, thank you. Then that is okay, right? Okay, dot product then we have a minus, but we have another minus there from the definition. And so what do you have? That is h omega square, right? So here that means h over r squared plus h squared. That is the torsion we have. And this is a constant as well, right? Because we take the r is the radius of the circle, and h is a constant from the z coordinate. So what is the meaning of that? Actually, the torsion is a constant. That h measures how much it goes. This circle goes up, right? We take the h positive, right? So what happens if h is 0? Simply speaking, h is 0, then case will be like a circle, right? So that actually you see the torsion measures how much the curve lies away from a single plane. So we have experience on the Frenet-Serret practice by these two examples. Okay? Okay. The next one, actually in this case so far, we are given the curve, right? And then we get the Frenet-Serret practice. But what about the other way? What happens if you are given the curvature and torsion somehow? then can you say something about the curve? If a curve is given like that, there's not much difficult to find out the curvature and torsion. Just follow the definition, right? But what about what happens if you have some information, like a curvature is 0? Can you say something about the curve? Straight line. We can guess, right? In fact, it is true. We have checked that any straight line has a curvature 0. And converse, if a curvature is 0, can you say that is a straight line? Answer is yes. Okay. Okay. Well, yeah, I'll do that. Actually, it is not difficult, but I think I need more time, so I'll do that one next time then. It's a review of those one. Okay.